two things that we need to first understand, right? We need to understand functions and we need to understand limits. Right? Those are the two things that you need in order to understand calculus, right? Two things. So what is it? You can take some z xy to some w uv. I'm going to use this notation constantly and have some function here, right? That's what you're calling a complex valued function. Maps from one complex number to another complex number, right? From xy plane to uv plane. So this is what it is. Nothing complex, right? You just have something, some mapping from here to here is essentially what you're trying to say. Cartesian coordinates xy, uv. So this is really what it is, right? Typical mappings, I will not go over this, but this is the domain, right? This is the range. Basic ideas, bijection, injection, surjection. Have ideas about those? Okay. So I'm assuming you know what is a bijective map, it's injective and surjective and things like that. So if there is a map, there is an inverse of a map, F inverse and all of those. Simple mapping funda, nothing great, right? Now if you take an example here, just take a simple example so that you are clear about what I'm saying. If I say f of z equals, let's say, z square, right? That's a function, right? So that is what x plus iy square is what x square minus y square plus 2i xy. Correct. This can be written as uv, right? Where u equals x square minus y square and v equals 2xy. Correct? 2xy. It's u plus iv is the u plus iv is the function. So u is this, v is this, right? Simple. So this is what it is. So that is how you understand. So what is this? And another way to think about this complex valued mapping is two real valued mappings, where u of x is x square minus y square and v of x is 2xy. Same thing, right? So a complex valued function can be seen as a mapping of two real valued functions. This is trivial, but this needs to be remembered because we will do this a lot and we will just claim that any complex valued function is just a combination of two real valued functions, which is what it is. Correct?
Yes.
Now we'll see limits. Now limits in complex numbers are, see again by this time you would realize one thing. We just use complex numbers, we pick the definition from the real world itself and then we just implement the same definition. We just implement the same definition in the complex world. That's all that we do, and such that. Yeah, thank you. So that's all. Nothing very great. Let's just talk about limits a little bit, and then we'll. Limits, there is a certain speciality which is a little bit subtle in complex numbers, which you may want to give a little bit of attention to. Other than that, it's the same thing. So how do you? Again, let us assume a function which is basically complex numbers to complex numbers from C to C. Okay. So what is it? So what does it mean if I say limit z tends to a? Okay, f of z equals n. If I write this, what does it mean? It basically means for all delta. Some delta that you actually take, typically greater than 0, then 0 is less than is equal to the modulus of z minus a less than equal delta. You have the other one as epsilon, right? for given delta and epsilon. This is what the definition is, simple definition, right? Where z minus a is less than some value, then function of z is less than some other value. Both of them are small values, then you can say that as z tends to a, f of z is equal to the limit, some limit n. That is all that this means. Nothing, again, this is same as real. Real also you will do the same thing. But what is the difference? In real numbers you have interval, right? R some, right? And then you talk about intervals, right? As between x is between this and this, function of x is between this and this, right? If f of x is x square or something, okay, as x tends to 1 or x. And then when you check the limit, you check it from both directions. If you are approaching the value from both directions, if both values exist and are same, then limit exists. Correct? That is essentially what is the definition of limit in the real number world. Everybody clear, right? There is no confusion here. Okay. Now let us see it in the complex world. In the complex world, the concept of limit is same, but when we talk about derivative, we will see a little subtle difference. This diagram you should get by hearted by the time I am done today. Right? Let us say some z naught maps to some w naught. Essentially what you're saying is if this value lies within delta, then this value should lie within epsilon. This is what you're kind of saying, that the limit exists to some L, right? This W0 equals L. Then the limit of the function is equal to L. That's essentially what you're saying. So it is not an interval anymore because it's a two-dimensional space. So it becomes a disk. Within, see, again a subtle difference, but it will be useful when we go to quantum computing is, we are not taking the boundary. It is a disk, not a circle. The moment you say a circle is on the circumference, this is not on the circumference, this is within the circumference. On the circumference is a special case that we will see later. But as of now, it is strictly less than, right? Less than delta, less than epsilon. So it is a disk, not a circle.
So the properties of topology still holds here. So
yes, it will be a disk. And that's, yeah, it may not look important now, but it is important to kind of know that funda. Again, everybody on the phone, okay till now?
Yeah, Srini.
Okay. So let us talk about derivative. So before we go into derivative, let us maybe talk about another concept which is useful. If you talk about f of z, what is it? It can be written as uxy plus ivxy. Correct? Similarly, L can be written as some L1 plus IL2. Correct? This L can be written as. So both of these are equivalent ways of writing it, right? Either you write as some function or L1, because at the end of the day, a complex number is made up of two real valued numbers only. So L1 and L2 are two real valued numbers. Correct? Similarly, here we are saying some Z tending to A. Correct? A also can be written as A1 plus IA2. Sorry, right? I will rub this out. I don't want people, because on phone it could be difficult for people to follow. Now we are saying limit z tends to a, f of z equals n. This is the statement I made. Then, if this statement is true, then what does it mean? Limit whatever xy tending to a1 comma a2 u of xy is equals L1. Correct? So similarly, L2 also, right? Limit whatever xy tending to a1 a2 v of x comma y equals L2. Equivalent statements, right? Till now I have done nothing. I have just told you what this is and what this is. So till now clear again?
Yes.
Okay. Now let us take the actual definition of derivative and then we will use them. Okay. We will use them in an equation a little later. But so I want to hear on the phone. Everything clear till now?
Yes, Srini.
Yes. Okay, good. The reason I keep on asking is, I know Raju is here, it's relatively easier for him. It's relatively difficult for you guys, right? Now, and tell me if I'm going too slow, I'll go a little fast, or if I'm going whatever, too fast, I don't think I can go any slower than this. This is probably the slowest I can. So now if you want to define what is the derivative, we'll again copy the real valued answer only. We'll just copy the same definition, right? We will not try and do anything fundamentally great. I will say, what is this? Limit delta z tends to 0. The oldest definition was f of z plus delta z minus f of, what is it? This is the definition of derivative, right? No confusion till here, right? It is just the derivative. Now, if we say if w equals f of z, right? That's what we have said. If w equals f of z equals some u of xy plus iv of xy, correct? Now, therefore, if you look at dw by dz, is what is this? That is what that is. Because this is nothing but delta w, right? This whole thing breaks in. The whole numerator breaks into delta w only, because you have just defined w to be f of z. So this just becomes delta w by delta z. Of course, if you break it open, it'll become whatever. If you kind of want to write it in a bigger way, then it becomes delta u plus I delta v divided by delta x plus I delta y. It is the same thing. Now, the difference comes here. See, this delta w by delta z for a given w and z is constant. Now think about this. I'll actually geometrically draw this. There's a little subtlety here that you should remember, which happens in complex derivative as compared to up till now. I've spoken nothing new. It is exactly the same thing as if you're trying to take a derivative. If instead of z, if I put x here, everything holds. Okay. Here, if I just make y equals 0, so this becomes only real. The whole thing holds. There is nothing here which is particular to complex numbers. But there's one fun thing that happens. And I think that fun thing will get into something called conformal mappings, which will be the bedrock of quantum computing. A lot of times we'll keep saying conformal, and I've seen people get extremely confused about that when I keep saying conformal mappings, okay? Let's try and understand this pictorially, because to me at least, pictorially, it's a lot better. Let's say there is some point Z, and there's some point Z1, right? You are approaching Z0, limit. So let's say you're approaching it from Z1. This is your delta Z, correct? As you are approaching closer and closer from a particular direction. Similarly here, you say W0 and you say W1, okay? The idea is, as if you are progressing this also comes closer and closer, or W0 or L. That will be the limit that you are saying, right? The function exists. So the point is now, you have called the derivative, which is to be equal to dW by dz, or equals delta W by delta Z, is what you have written here. And you said if this exists, then the limit exists, and this has to fall to that limit L, this ratio, as delta Z is becoming lower and smaller and smaller and smaller. Now what happens if you come at Z0 from another direction? Let us say this is Z2. You are coming at Z2 from a different direction, and let us say Z2 maps to W2. Right. The idea is, within this circle of epsilon, whichever point you take, they should all tend, right, towards W0. That's where you say that the limit exists as you take this within delta. This is what we defined here, correct? Now there is a problem. Not that there is a problem, but there is something very, very funny that happens within complex numbers. The proof of which may be outside the scope, but we'll see. The thing is, if you talk about real numbers, real valued numbers, okay, the limit should exist for the derivative to exist from any direction that you approach it. Right? But the values need not be same. In complex numbers, you will find out that irrespective of whichever direction you are approaching Z0, not only will the limit exist, but the value will be same. Just think about it for 1 second. So you have a point here. This is mapping to another point here. Now you take any point here, whatever, and you start approaching the point. Then, as you are approaching this point from any direction, the value that comes out will be exactly same. the derivative value will be same. It is f dash z will be delta w by delta z for all directions of z naught. Whichever direction you apply from this value will remain constant. This doesn't happen in real. In real numbers, the limit will exist, but it need not be same, which is an important distinction in complex numbers. See, this results in something called Cauchy-Riemann conditions, which we will see a little later, why this will result in Cauchy-Riemann conditions, okay? But this is important. This is very, very important condition that happens within complex numbers. It does not happen with real numbers. It does not happen with any other number system except with complex numbers. And this gives rise to, not only in quantum mechanics or quantum computing, all over physics this is used heavily, and we'll talk about a little bit where it is used, because I think you will say Srini is telling us all of this, why is it useful? So we'll see where all it is useful.
Any significant reason for being the same?
Yes, there is a very significant, actually, there is a very, very significant reason, okay? We'll get to that. That actually results in a proof of Cauchy-Riemann, actually, what you're saying, okay? So yes, there is a very significant reason on why this happens. And this happens only in this case, only in two-dimension disk. It doesn't happen anywhere else. It happens only in a two-dimension disk, okay? That's why I keep saying that nature has been very good to us. If we are put in a four-dimensional world, this math wouldn't work. Nothing of this work. Because we are in three-dimensional, because complex numbers are in two dimensions, this works. And we'll actually see the special cases of why that works. Yeah. Is that clear to the people on the phone?
Yeah, Srini, follow.
Good. So now let us just do this for two cases. Okay, I will just do it for two cases where delta y equals 0 and where delta x equals 0. Let's just see those two special cases and we'll see why those two special cases are useful. That means we are only on the real line or only on the imaginary axis. So the other axis is removed. How does this look like? It's important to kind of see that. Okay, it gives you a little bit more intuition, and we'll get to the Cauchy-Riemann equations of all of this story was to get to Cauchy-Riemann equation. Okay. So case 1, let us say delta y. I could not get much time to prepare on this. Actually, last 2-3 days I've been watching too many movies. But yeah, you guys watched any movies and stuff? Nobody? Did you guys watch 83?
Yeah, Srini.
Watched it. I really loved that movie. It was very, very nice. Yeah, I watched too many movies. There's actually on Netflix, there's a show that I watched. It's a Malayalam show. Superheroes. It's very nice. I don't know, you guys. Yes, it was awesome.
The Great Khali appears in it.
Huh?
The Great Khali appears in that.
Yeah, no, I haven't.
No, not that one. It's a Malayalam movie, Minnal Murli.
Oh, Minnal Murli is very, very good. It's
Great Khali is there in that, I think.
Okay, I'll watch it. It's the best superhero movie I watched. I don't know if it's a movie or a show, but it's a Netflix production. Okay. Right, when I said delta y equals 0, what does this mean? It means you are approaching z0 only from, z0 only from left or right, because the imaginary axis is 0. So what is it? This is what? This is basically the same story. Limit delta z tending to 0. You have what? Delta u by delta x plus I delta v by delta y. Correct? Correct, because we said this is what it is. No, delta x plus I delta v by delta x plus delta v. That's how we kind of defined it. So it just means that you just differentiate with respect to x, because this doesn't exist. So it becomes some partial derivative of u with respect to x plus I of partial derivative of u again with respect to x. Ante kada? The reason you have to take two partial derivatives is because it's a complex number. It will have to end up being x plus iy. Otherwise, it is not a complex number. This is at some x0, y0, whatever, if it is set 0. But that is 0, but doesn't matter. Correct? So this is the partial. So, and we'll see why that comes up when you kind of do the Cauchy-Riemann. But so this is clear, right? Very simple. I'm not trying to do anything complex. I'm just hoping you are understanding the chain behind my thought as I'm doing this. Okay, nothing. You do case 2, you do what? Delta x equals. So that means you're approaching Z0 only from top or bottom. Again, if you write what? Same thing, because delta x is 0, right?
So you partial derivative.
Again, partial with respect to y, but because it will come like something like this, right? It will come some dv partial derivative plus whatever. You kind of multiply by I by I. Oh, this will have I2 here.
Previous case.
No, not in the previous case. In this case, because you are doing it with respect to y. So it will be, and then I you multiply, you will get a minus here. You have to do some small algebraic nonsense here. So you will actually get minus I dv by dy. That's what you will get. Here you will get a minus because I square multiply karna padega dono side. Okay, there will be some. Now you combine case 1 and case 2, the other equation and this equation you combine, because both of them have to be same. That's what I said, irrespective of whichever direction you approach the same point, the function, the value needs to be same. That is what I told last time, and that is the key. If you combine this equation and this equation, the previous one and this, which this can be 2 and the previous can be 1, if you combine both of them, you get what is called the Cauchy-Riemann equations. Okay, and this is very important. I'll explain, and I think you will have to initially just remember them. Okay, and slowly, when you are getting into quantum computing, especially Toffoli gate and things like that, you will slowly get to understand the meaning behind it. But for now, just remember. Okay, if f of z is differentiable at z0, it is called analytic, basically. Okay, you would have read analytic functions and all that. That's what this means. If it's differential, it is analytic. Okay, and what this means is u of x, and if it is written as whatever, z equals u plus iy or whatever. Sorry, not y, iv. Then ux will be equal to vy. The partial derivative of u with respect to x will be equal to the partial derivative of v with respect to y, and partial derivative of u with respect to y will be minus v partial derivative of x. This is what is called the Cauchy-Riemann conditions for differentiability. This is, if a function satisfies this, function is called analytic. The function is called differentiable. This is what it is. This, most people would, I don't know, be taught somewhere when you're taking a complex analysis or real analysis course. This is known as the Cauchy-Riemann conditions. And if you have time, you can prove it. The inverse also. The inverse also is true, which is if this is true, the function is differentiable. It is not only that a function is differentiable, this is true. The inverse is also true, which is if this is, and that is how you actually do real math, where you see these conditions. If these partial derivatives hold, that means the function is differentiable. The first order differentiable. First order differentiability is guaranteed. Of course, there is another famous theorem, if somebody remembers, if there is a first order derivative, the n order derivative exists. Okay, there is another very famous theorem by another very famous man. Even if you guess it, you will be right. You will be right. Who is the? See, at this time in mathematics, there are only few people you should remember. You should remember Euler, remember Taylor, remember Laplace, remember Cauchy, remember Riemann. You most probably have got the math right, because these are the only people who are doing useful math back in the time. So it is those are the Taylor conditions. Okay. It is a polynomial and things like that. But anyway, so that's a Taylor condition, but this is the Cauchy-Riemann condition, very, very important.
The Taylor series.
Taylor, the man who did Taylor series, he has got the Taylor condition, which is if there is a first order derivative, he says nth order derivatives exist. If it's a polynomial, or if the coefficients are rational, that's okay. I don't want to get in that and not confuse everybody. But if you think about it, the same thing. The very important conditions. Anybody seen these conditions before, or is the first time in your life you are seeing these conditions? No answer, huh? Okay, let's take a couple of examples. Guys, nobody has seen this function before? Why don't you speak up, man? It's like I just speak like a college professor only nowadays. I'm bored of this. Okay. Z square. So what is U? What is V? What are these partial derivatives? What is U with respect to X? This somebody tell me, boss. I am not going to do this. Tell me. What is partial derivative of this is U, this is V. Partial derivative of U with respect to X क्या है? 2x, right? You got to speak up, man. Otherwise, I won't take this. I'm telling you from next time. What is Vx? With respect to partial derivative with respect to x.
2y.
Good, a little late. Now, not you, somebody from the phone, I need this answer. What is uy? Partial derivative of u with respect to y?
Minus 2y.
Good. What is the last one? Partial derivative of v with respect to y?
2x.
2x. Now, does this condition satisfy? Is the partial derivative of u with respect to x equal to the partial derivative of v with respect to y?
Yes.
Yes. Partial derivative of u with respect to y, is it minus of the partial derivative of v with respect to x?
Yes, yes.
Yes. So the Cauchy-Riemann conditions are satisfied. Correct? So fz equals z square is differentiable, is an analytic function. You can take any function and prove it. So this is the way. Of course, we take simple because in class teachers don't want to take load, so we take simple things. When I give it in an exam, it will not be z square. I'm not going to have an exam, but it's not going to be z square. There I'm going to complicate it. I'm going to get e and I'm going to get sines and cosines and have fun. But the way to do it is the same, right? In the class, I don't want to. See, anything that you learn, you will only learn if you do this, if you practice it, if you go ahead and solve a few problems. I don't know where they will exist, but I will give you some problems if you want me to. But you have to solve it. If you don't solve it, I'll teach you today. 1 week later, if I ask you what is Cauchy-Riemann, nobody will remember what is Cauchy-Riemann. Okay? Everybody is like just gone. Even when you see movies in between and you want to remember, you have to solve 100, 500 problems. Then only you'll remember. Unfortunately, otherwise, kuch nahi yaad rehta. Now I'll give you a good example, an example which probably will Be useful. After that, we'll see its application in generally physics and in our own quantum computing. What sort of places will we actually use something like this? Now, let us say f of z equals z complement. I spoke to you, or z conjugate. I spoke to you what is a complex conjugate, right? What is a complex conjugate? Of x plus iy is x minus iy, right? So let us say this is the function. The function is the complex conjugate. Now, if you want to calculate what is u of x, okay, first don't get confused. You'll get confused. U equals x, v equals minus y. Correct?
Yes.
So what is, let's see, Cauchy-Riemann conditions. What is u of x?
1.
What is u of y?
0.
Or maybe u of y? 0. Some
Y is 0.
What is v of x?
0.
What is v of y?
Minus 1.
Now tell me, Cauchy-Riemann condition ux equals vy?
No.
No. And uy equals minus u of x?
No.
Correct. So, complex, this is a very, very important result. You should by heart it, literally, because it comes all over the place. The complex, a function that is a complex conjugate is not differentiable. It looks very, very ridiculous, no? You would say x plus iy is y is x minus iy, not differentiable. It is not analytic. And this will come all over in something called the Toffoli gate within quantum computing. This is what will come through again and again. It is not analytic, it is not differentiable, it's not reversible, and we have to do a lot of drama for this. And this has no, how do I say, counterpart in the real world. Complex conjugate is a very complex thing. It is not, it has got no, I cannot say that this is like a negative number. No, it is not like a negative number, right? It's not like negation. The negation of x plus iy is minus x minus y, minus iy. So this is something that exists only within the complex world. Here, the problem is, and I think it will be a homework, if you want to do, you can draw out these things and practice. Here, what will happen is the directional derivative actually exists. Just that the directional derivative will not be same in every direction. I told you this, right? In complex numbers, the thing is, not only should the directional derivatives exist, but the directional derivative should be same in every direction. For this example, that will not hold true. The directional derivative will exist still. In every direction it will exist, but it will not be the same, and hence it is not analytic, which is a very, very particular attribute of dealing with complex number differentiation as compared to real number differentiation. This is the only thing which is different. Other than that, everything else will be the same. But this only different thing is very, very useful for us. Now we'll talk about a particular usage of this, which in physics a lot of, because I see a lot of people, even when I taught this class, not this particular class, but I was teaching something else, at Engineering Staff College of India, they were all like, why should we learn about this? This is Kalab kya hai? These were all big people. They were all questioning me. You are teaching us all of this. We never got it 20 years ago, and why we have to do it now? See, this is just not made up for you for fun's sake, right? I don't know if do you guys remember this particular equation? It's called the Laplace equation, okay? Which probably some of you do and some of you don't. I don't know. D square u no this Yeah, by dx square plus, actually it's partial derivatives in Laplace equation. I am sorry. D square u by dx square plus.
Dou square u by dou x equal to 0.
Remember this equation? Guys on the TV, or guys on the, not on the TV, on the phone, anybody remembers this?
Came across this.
What?
I did. I think I came across this.
Yes, I would be really surprised if you hadn't, Dheeraj. All of you would have, except maybe Madhu. Madhu, you didn't study engineering, right?
No, I didn't, but I have come across this.
Oh, yeah. This is a very, very famous equation. It's called the Laplace equation. It is typically used for solving the temperature problem, but it can be solved for many, many things. In thermodynamics, you would have come across this, but you would have come out in electromechanical theory, in mechanics, in so many things you would have come across this. Okay, and this is not V, by the way. This is also U. So U can be substituted for anything. U can be temperature. U can be the radiation. You can substitute. The power of this equation is you given some initial condition of this. In some cases, you will see as d square t, where they will write temperature. But the thing is the same. This U can be whatever. So anywhere where there is an initial condition where some U naught is given in kind of as some function of x and y of some initial conditions, and then you have to say that over time I want to understand how this U naught is distributed. If it is heat, you will say on some surface you are given at this point x and y, the temperature is some 100 degrees. How is it spread across the surface of the material? Same. How it is spread is it satisfies this condition. And how do you derive it? It is very simple. If U plus IV is analytic, you can actually use Cauchy-Riemann equations and you will get this. It is straight derived from here. If you say that this particular thing can be expressed as a complex analytic function, this comes straight out of it. I don't know if people who have proven it will know. It will have some 8-page proof in classical mathematics. Okay, I have a huge proof to prove this. If you take it as a complex analytic function, it's a 2-line proof using Cauchy-Riemann thing. But the only thing is Cauchy-Riemann came about 50 years after Laplace, so Laplace couldn't use that. Sorry about that. His equation came a little later. But you can also do, and the converse is also true. Right, the same thing. So you can get from this you can also get this. So whichever way. So this is so very useful to you. Anything that you want to understand how a particular variable is distributed in space or time, it will satisfy this condition. Okay, this is a beautiful thing. It works in mechanics also. You can also figure out the position of a ball, the acceleration of whatever, everything you can find out using this. In fact, when you have some time later, I'll talk about something very, very interesting. It's actually Lord Kelvin. All of you might have heard about Lord Kelvin. There's some very, very good work he has done. What is Lord Kelvin famous for mostly?
Absolute zero.
Absolute zero. It's known as the Kelvin scale, right? But he did some other interesting work also, more specifically around understanding what was the toughest problem for close to 1,000 years in Europe mathematically, was understanding or predicting the height of tides. Because ships would run aground, right? If you want to get a ship on, you would want to know high tide, low tide, because typically in a day there will be 2 high tides and 2 low tides. Madhu, you might remember, or Anik, you might know. I don't know if Calcutta still does it, but back when I was a kid there in Statesman, you always used to get the times of low tides and high tides. Every day you will get 2 high tides and 2 low tides. They'll also give you the height. You know how that is calculated? That's a phenomenal application of this theory of how those high tides are actually calculated. Let me talk about conformal mappings. If I have some time, I'll talk about it. Okay, that's a very, very interesting application, and parts of it are useful for our quantum thing also. Anyway, so Yeah, you should. See, math is very interesting. A lot of people tell me, why should I learn it? My question is, if you don't learn it, you can't solve most of the problems in the world. Because most problems in the world will end up being. Okay, I hope there's some intuition about Cauchy-Riemann conditions. So just, if not anything, just memorize them. Because the next time I'll go through this, I will not explain that it is Cauchy-Riemann conditions. We will just take it for assumption, and that's how we will say we are going to kind of design this gate or something. Okay. Now we'll talk a little bit about what do we mean by conformal mappings. And again, this is an unfortunate name. Okay. In terms of conformal mappings, maybe we should say conformal functions at this point. Okay. Because we will be dealing with only those mappings which are functions. But the reason it is called mappings is there is a whole superset of mappings which are not functions.
So in a real number one, so for checking whether if it is a function is mapped to a domain or not, so we'll do have some sort of a vertical line testing. So can I assume that this will be a method where I can say whether this function belongs to the domain or not? So
Belongs to the domain or not? I didn't get you. Okay.
Okay. For example, in real number one, so we have a vertical line testing it. For example, a particular function belongs to this domain or not.
No, here you don't do that. You don't because it is two-dimensional. You need a third dimension to do that sort of test. You do a simple ratio test or something like that. You don't. Yeah, in two dimension, I know what you're saying. F of x is x square, for example. You're plotting different values and you're kind of plotting it, and then you're saying, hey, this is the shape of a hyperbola or a parabola or whatever like that. Of course, in xy plane also you can do that, but then that has to be seen in the third dimension, right? The height of this. You will get the shape, but see, in one dimension real number, this gives you the area.
Yes, correct.
Okay, in here you will need something else beyond that to get the volume.
I mean to say, do we have any other approach for figuring out by looking at the expression itself? I mean, like line test for real number one. So
No, you don't have.
Okay.
You don't have anything equivalent like that. Yes, that's a good question. You don't. You don't have. Yes, I know what you're saying. With my question, I don't remember of anything like that. So anyway. See, there is something called local inversion of a function. See, let us talk about this in the real world. Now, in the real world, or whatever, let's say there's a point and you kind of map the point to something else in your real world, and you keep that mapping or whatever. Actually, it's one dimensional, so let's not try and confuse this. I don't want to have two dimensions. In the real world case, you're not doing it in two dimensions, right? You're just taking this and you're taking this and you're doing some mapping. Correct? Now, this is some f of x. When do you say there is an f inverse of x? When the mapping is bijective. Correct? Bijective map can be inverted. And so this part here, right? Everybody knows what is a bijection. 1-to-1 and onto. Okay? It is 1-to-1 and onto mapping. If you have a 1-to-1 and onto mapping, you can inverse this. It's an invertible function. Now, let us see the problem here. Now, let's just say you have, again, let us imagine we are in the real world only. Okay. Let us say there are these two vectors, these two lines, okay, which are real valued functions, some real valued functions which exist, and you are trying to map it into, there is some function that is taking these two lines and it is mapping it into this subspace, into this area. Okay, this is all real. There is nothing complex here, right? So B is B, A is A, some XY plane, and you are kind of mapping. Now, is this function invertible? This is a one-to-one and onto function, let's just say. That means everything here has a unique point here and everything here has a unique point here. If you try and invert this, if you try and create an inversion to this, there will be there will be some points here which will not, if you completely invert it, there is no guarantee that this angles will be maintained. Here it is 90 degree. Here it is some theta which is less than 90. All the points will come back, but the angle will not be. For some points, the angle will be maintained. For some, it will not. There is no guarantee that this inversion will actually maintain the angles when you're doing it like this. This is a one-to-one and onto function, so it is invertible, but it is invertible that each point here will be uniquely mapped to a point. That guarantee is being given, that guarantee will be satisfied. But that does not guarantee that the angles will actually be maintained. You guys, you understand the problem here, right, that we are trying to solve.
So basically
the shape will be some shape.
it
is not, this also will be one of the possible answers, but there is no guarantee that you will get exactly this shape back. You will get some shape back. Okay. What does one-to-one and onto inversion guarantees? It only guarantees unique points. You will get unique points, but there is no guarantee that these angles will be maintained when you are getting back. Okay. And this is a big problem. This is a big problem in physics. It's a big problem largely in physics only. So why is that a problem, right? So for example, like I told you yesterday, or just now, there's some thing that you're trying to measure the heat distribution of, and this is an irregular shape. It's a painful shape. Let us imagine you can happily map it into a square shape, solve the thing here and come back. Then it will be lovely, you know. It will be, you're solving your problems is so much fun like this, so much simple like this. But this doesn't guarantee you, unfortunately, that you will get back this shape. You will get some shape, but not this shape. Hold on, I think I have been thrown out. Kya ho gaya? Okay, I think we were lost for a second. Now it's okay, guys?
Yeah, Srini.
Yeah, hello. So you understand why this is a problem, right? So when it doesn't maintain the angles, okay, at which these vectors that you're trying to create a mapping for, then there's no guarantee that you will get this shape back. You will get some shape back. You may also get this shape, but you may get some other shape. And why is that a problem? Because in a lot of physics, we want to change the coordinate systems and we want to map it back once we solve the problem. We can't necessarily do it with this. Now, what I'm saying is, again, there are some proofs about this, which I will not. There is something called local invertibility. Okay, the local invertibility just means that, see, if this is the XY plane, okay, and if let us say this is the UV plane, right, that you're kind of mapping into, then what it says is the partial derivatives of UV with respect to XY, the determinant of that, which in this case will become a Jacobian because you've got multiple partial derivatives. If it is not equal to 0, okay, then it is called locally invertible. That means for some epsilon distance here, that shape is being maintained like that. But unfortunately, what will happen is some places this will get 0. And wherever that Jacobian gets 0, you will not get the shape. But anyway, this is got nothing to do with complex analysis. This is just linear algebra, real analysis type subject. Okay, so I will not get into depth here, but for you to just understand, when is a mapping invertible? When a mapping is invertible, when the Jacobian of the partials is not equal to 0. Okay, that's all.
Like how in matrix is a singular matrix and
Exactly. Positive semi-definite. It has to be positive semi-definite. When you're trying to look at the curvature, you say the Hessian. The second order derivative, again, the Jacobian of the Hessian is positive or is negative. So this is just, I think you should get a little familiar with partial derivatives and Jacobians if you are not. It's not very difficult, I guess, just a question of following up some basics. See, again, don't get confused. This is a determinant. The only reason I'm calling it a Jacobian is it is not 2 by 2. It is some n by n, right? Because I don't know what dimension is u, v, x, y. I am just saying some partial of u, v with x, y. That's all that I'm saying. So that's the only reason, okay? Now we will show, maybe I don't need to show, maybe I'm running out of time. I'll just tell you that because showing it will take a lot of time. If a complex valued function, okay, say I think just take the result. I think we're already at 12 o'clock. No, I want to finish something else also before I go. Yeah, 11:59. I will not prove this, but maybe if I have time, next time I will prove it, or maybe a little later. But see, the thing is, now we want mappings to be conformal, and you know why. And I'm saying it will not be conformal because this partials will not be equal to same. But complex numbers have a fantastic principle. If a complex valued function is analytic, it is conformal by definition. So it will preserve angles. Why? Again, the same property. The value of the limit, the directional value of the limits not only exists but is same. It is because of that one property that complex analytic functions are conformal by their definition. And if something agrees to the Cauchy-Riemann conditions, it is not only analytic, it is also conformal. So Cauchy-Riemann conditions are more powerful than just derivation. Derivative exists, but those functions are also conformal. So now I can do fun things. I can just move stuff, and that is a property that we will use again and again in quantum computing, where we will take certain functions that we have to solve for. We will move it to a conformal mapping, which is a very, very easy mapping. We will solve it there and bring it back here. We will keep on doing it. We'll take the advantage that a qubit can be expressed as a complex number. In fact, if you ask me, that is the single most important reason why a qubit is expressed as a complex number. Because it lets you take advantage of the conformality of functions. All analytic functions in the complex world are analytic or conformal. And you can prove it. You can prove it just from the Cauchy-Riemann conditions. Ux equals Vy and Uy equals minus V of x. You just take this Cauchy-Riemann conditions, and with this you can prove that, actually speaking. And you will get the proof. And also, one more thing, complex qubits, what did we say? R theta, right? You can express a qubit as a R theta. Conformal mapping preserves theta. Theta is the phase of a qubit, right? Phase of a photon or phase of an electron or whatever that we use. It's finally the phase. So it helps you preserve phases as you get them. We will do multiple order of this, like we will move it to one space, from there do some calculation, move it to another space, do some other calculations, and then simply keep inverting back. Okay, and all of that is possible because of that one property that complex numbers have. The directional derivatives not only exist but are same. This is an incredibly, if there's one thing you can take out of this class, remember that. Don't forget that, because that is the key for everything. If somebody asks you, why is this true? Many people will say, oh, that is how it works. No, not that is how it works. It is true because of this property of complex numbers. Okay, so there is a lot of other proofs and stuff which I will skip right now, but if you want to get through, I think I have told you the important bit, okay, which is what it is, maybe before I get into quantum. And how much are you guys, like, do you want me to go deeper into this, or you want more interested in the, because I was thinking you're more interested on the quantum side, and this is just for me to give you a background, because this complex analysis itself could be like forever. So how do you guys want to do this? Do you want me to go more depth into complex analysis or get into quantum quickly? And then maybe as required, you will end up revising.
I think so. It's important that we do this because it'll feel shallow or else trying to understand that without understanding this.
Okay, ठीक है. Anybody else has a different opinion?
Go to a level where it carries the same fundamentals to the next level.
Okay. Yeah, I think which we have done, maybe a little bit more like, okay. Anybody else has a different opinion? Please let me know. Huh? Okay. People seem to be very, very happy. Oh, what else do I have to do? There's a little bit of this. I won't get into too much details again. Sequences and series, we probably have to do a little bit to understand what this means in the complex era, right? So, e power z. Correct. Sin z. Some important questions, right? Again, I think by now all of you would have realized the way to do it is just take the real value definition and plug z. And then see, because I think that seems to be the best way this thing works instead of, so what is e power x? I won't derive this. I hope you guys remember this, right? So this is how you can write exponentials. E power whatever, Euler number to the power x can be just written as a Taylor series expansion, as an infinite series of x power n by n infinity. So what does this mean? Now, instead of x, I can just put is this the definition then? Very, very simply, I just replace x with the z.
So the fastest all comes to the sine part.
Yeah, again, when you have sines, you have -1 to the power n, right? The power x n by something. That's how the sign will get defined. The only thing you do is corresponding values are plus minus, plus minus, plus minus. That's all that you will do. That's why you will get that whole e power I pi. -1.
So yeah, +1 equal to 0.
Plus, yeah. This is how from you will derive this and you will put this in, and this is the famous equation that you will actually get. So I will not get into all of that. I think that is all pretty self-explanatory at this case. There are ratio tests you can do and all of that. But see, one thing you should remember, okay? So if you actually write it like this, okay? See, there is one thing that you should, okay, there's one derivation that I will do, which is important, okay, out of all of this. The rest are all kind of the same derivations and all of that, nothing great. Sin z will come the same, e power z will come the same, but there is one equation that we will use again and again, okay. Now, e power ix. Okay, and I think this derivative everybody knows, but or e power x can be written as cos x plus sin x, right?
Yes.
in terms of when you actually do the Taylor series expansions, this is what you will get. E power x can be written as cos x plus I sin x. Now, subsequently, you can write e power ix equals cos x plus I sin x. Okay, from this you can derive this. Now, what can this mean? You can actually write this because this is nothing but a complex number, right? U plus IB. On this side, you can write r theta for this because that's another way of expressing this, right? And then you can say r cos theta, right? You can say r cos theta plus I r sin theta. So if you take r out, becomes cos theta plus I sin theta. Again, what is this substitute? E power I theta. This is a very, very important. Z can be written, or a complex number can be written as r e power I theta. This is again a very, very important way of writing a complex number, which we will again and again use. So complex numbers, three ways of writing: x plus I by r theta, or where r, whatever, the magnitude is r and the argand is theta, or r e I theta. And this is the way we will keep writing a lot of times because it's a simpler way. I just wanted to derive this very simply so that this is something that we will use when you are trying to do a lot of quantum computing thing. You will say complex number equals r e I theta. See, but here there is one problem. Okay, when I say r e I theta, it is actually theta plus 2 pi k. Right, because every time it's 360 degrees, it becomes the same theta. Correct. So it is 60 degrees. 60 plus 360 is also 60. Correct. Because you make a whole turn and come back again. So whatever number of k, so this function is actually multi-valued. And this is one problem you will get when you are talking about complex numbers, because this function is multi-valued. Because theta, when I say theta, theta is whether theta is 30 degree or theta is 390 degree or theta is whatever 750 degree. They're all same.
What is k over
Some integer, multiple. This is here k is some 0, here k is 1, here k is 2.
Okay.
Correct.
Fine. Okay, got it.
So you just keep doing it. No, you understand what I'm saying, right? There is one problem though, writing it like this. It's a multi-valued function because how many ever circles I take around that circle, that keeps happening the same thing. Because 2 pi is just 360 degree, one whole circle. And this is very, very important when you get into quantum world. Okay, because these phases, as you change the phase of the quantum particle, the energy levels change of a quantum particle. So you have to be very, very clear. Typically, we say the principal theta. We have a word for that in quantum computing. We say principal theta has to be minus pi less than theta pi. So that you're explaining the principal theta. After that, you can put case whatever, but what is the principal value? Minus 120, plus 120, whatever it is. In terms of degrees, it's minus 180 to plus 180. In terms of radians, minus pi to pi. Okay, but it's nothing great, but you have to remember this, because a lot of people will forget this. When they're solving, you will say, I have got one answer. You haven't gotten one answer. You have got infinite number of answers, of which anything that satisfies this is an answer to this. Right. So that's kind of an to ground us in terms of what we do and what we don't do. Now, there is one other important identity that we will use in quantum computing, which you should probably know. Hyperbolic, right? Hyperbolic functions. We use a lot of hyperbolic functions. People are familiar with hyperbolic functions, I'm assuming. I'm not going to define hyperbolic functions at this point, but if you're not familiar, just go back and read hyperbolic functions. So, for example, cos IHX or cos HX, right? How is cos HX defined? First forget I. E power x plus e power minus x by 2. Correct? This is the hyperbolic function. The hyperbolic function of x. Cos hyperbolic. Okay. I think all of you have seen this, no? Tan HX, sin HX. What are hyperbolic functions? Instead of a circle, normal ones are a circle, these ones are on a hyperbola. So that's it. It's the hyperbolic functions. Okay. So if you put cos IHX, nothing, e power IX plus e power minus IX. This is the, now expanding it in terms of sines and causes. If you actually solve this, solve not this, if you solve the imaginary hyperbolic function, you know what will the result you will get? And I think it's an exercise. Solve it. You will get cos x. So cos hyperbolic x in the complex world turns to be just cos x. Why? Actually, there's an intuitive understanding to this, right? Hyperbola. Hyperbola is what? X square minus y square, right? What is a circle? X square plus y square. Cos x is a circle. This is the hyperbola. In the complex world, x plus iy square becomes x square minus y square. No. So if you actually multiply this, if you actually solve this, that's why it finally results into a circular function from a hyperbolic function because of I. Because of I. And it's an important intuition to understand. Okay. You can solve this. This is not a big deal. You just write the expansion of e power ix and write the expansion of e power minus ix in terms of sine and cos. And just solve it. If you solve it, you will get the answer to be cos x. Now that is a very, very useful result again to remember. The hyperbolic. Sine and tans we won't worry that much, but this we will use for this identity because it will be useful for us to use. But you should probably try the write the hyperbolic for the sine also. That's just a minus here. Okay, and then solve it for sine and cos also. Just so that you're happy. The sine will not come out so nicely. The sine will come some value. It won't come out as nicely as cos x, but you can solve it for sine also. It's just for you to get some exercise. See, that's the other thing. Whenever somebody teaches you trigonometric, always learn the corresponding hyperbolic. And that tells you, see, trigonometry is really a circle. Hyperbolic is hyperbolic. And you will start understanding the cases when this degenerates into a circle. When two hyperbolas will degenerate into a circle, right? Because that's what happens. Hyperbolas degenerate in some specific conditions. And why hyperbolas? Hyperbolas are what? Two inverted parabolas. Basically, this is a parabola. Two inverted parabolas, you have hyperbolas. Again, I don't want to get into too much of it, but if you read Copernicus, he will come into such problems only. When he was trying to get to the planetary motion equations, he will get a lot of terms which will be x square minus y square, x square, which are a big problem. What is this guy calling me for? Yes, Vishwanath. Yes. No, it's the same thing. Send across the same thing. And yeah, and from next time, call me a day earlier or something. Yeah, okay. No, that's okay. That's fine. Thank you. Yeah, it's the same thing. Just send it across. Yeah. Where was I? Okay. Anyway, that's just a condition that you should remember. Yeah, now there are a lot of proofs that you can do, but I don't want to get into all of that. Yeah, there is one particular condition which maybe we will talk about. All of these are, again, maybe a lot of times and things like that, which you can do. See, if you actually take, and this is again something that you can do in your free time and see a little bit. I don't want to prove this in class because it's a lot of time. If you look at e power z can also be written as e power x plus iy, which can be written as simply e power x into e power iy. Which can be written as e power x cos y plus sin iy because you're just multiplying. Because and then this can be written as, so your ex, e power x cos y can be taken as u, and e power x I sin y can be taken as your v, and your mapping, right? This is 2. And if I have to prove that this will end up being a conformal mapping. Again, to prove it is just take the Cauchy-Riemann conditions and you can prove. Okay. But this is very, very important because what does this tell you? This sort of mapping tells you is, see, you can have something like this. Again, prove it at your own leisure. But one reason why I'm telling you in quantum computing this is important is you have some sort of grid type structure, right? E power z, some sort of structure, and you're trying to map it into a function space, which is more happier for you to work through and do your calculations and things like that. Here you will get a set of concentric circles. This sort of functions will give you concentric circles back here. So you can do a lot of useful work here and then invert it back. And this will be very, very useful in quantum computing once again, as you are trying to build some sort of NAND gates and things like that. You will actually resolve it here and solve it back here. Anyway, I think maybe it's too early for you. Maybe when we go there, we'll see. But for now, just try and prove these sort of things. Just write a few things and prove it on your own. Okay. See, the only other thing that I will try and tell you is this. Okay. I don't know how much familiarity you have with series. Okay. But two particular series become very, very useful again when you are dealing with complex numbers. See, 1 by 1 minus u, if you actually look at this series, or 1 by 1 minus x, what is this? It is 1 plus u square plus. It's an infinite sum. Okay, you'll get an infinite sum where sigma n equals 0 to infinity u power n. This converges when the modulus of u is less than 1. Makes common sense, right? So see, when u equals 1, this is simple. When u equals 1, this will not work. Correct? Because it division by 0. U is less than 1. This converges to 1 by 1 minus u. Okay? You can check that out. It's by simple ratio test. You can do that and you will get the answer. Now, let us look at this. Let us look at 1 by 1 plus z square. Now, this is a funny one. This can be written as 1 by z plus I, z minus I. Correct? Now, at z equals plus or minus I, this has a problem. Correct? Now, geometrically try and understand this. If you have a unit circle, this is some z value. Let us say this is plus I and this is minus I, right? Unit circle. So plus I and minus I. So what you're saying is this is a very weird thing. On the x-axis, see z has both x and y components. On the x-axis, let us say this is minus 1 and this is plus 1 of x. Here it has no problem. You can expand this circle to whatever length and this equation will make sense. But it has constraints here. So if you are looking at purely from a real basis, you will not understand this constraint. You understand what I'm saying? Because the constraint is here. Ikkada it can move. At x equals minus 1, this has no problem. This will work perfectly. But x equals minus I, it has a problem. Because it becomes 0, division by 0. So this also will result to something like this. If you actually see this, this will result to sign. Okay. Actually, if you actually try and write the thing, it results minus 1n z power 2n, which is actually nothing but sine theta. Which is actually nothing but sine theta. But it is a problem at plus I and minus I. So other than that, it expands everywhere. Essentially, what I'm saying is, when you get these sort of problems, complex numbers gives you a better vantage point to look at this. You cannot understand it looking at real value, because if you look at real value, this is perfectly fine, but the constraint is here on the plus and minus I, hence you cannot expand. Okay, this was just for me to tell you that complex numbers sometimes on the real line, even when you get into physics or you get into wherever, you don't see an apparent problem, but you will see that the equation will not have solutions at certain points. And the reason it won't have is because the constraints will be in an imaginary plane and not in the real plane. And you got to be able to remember that when, because this thing 1 plus z square at top of my head, I would think this will have no problem anywhere. This is 1 plus z square. What is the problem if z is 0? No problem. I still have 1 by 1, no? Because that's how you will actually look at 1 minus u. I will immediately say it's a problem. Because I will say when u equals 1, I have a problem. Here I will say, what is the issue? 1 plus z square, for everything it is valid. It is not valid. It is not valid on the imaginary side, not on the real side. And you have to be able to think like that. Okay, and it's just little counterintuitive for people coming quick into this like recently. Okay, so that's why I wanted to tell you that. Yeah, there are a few other things, but I think this is, see, the couple of things from today's class for next time on quantum when I get into that you have to remember is the conditions for derivatives, which is the directional derivative needs to be same in every direction, which is very, very important. That results in Cauchy-Riemann conditions, which results in conformal mappings. If you remember just these 3 points out of this class, I think I have done good. Okay, the rest of it was some math reaching there, but the real key point is those. Okay, and Laplace's equation is also important, but Laplace's equation will come again and again in which way. You don't have to remember that. But the Cauchy-Riemann conditions, remember ux vy and whatever u of y minus v of x. Okay, it's not something to forget. Okay, and maybe you have some time. I wanted to talk a little bit on what else I wanted to say today. So there's something else I wanted to talk, but that was more on machine learning side, because I was actually taking a class this Saturday for some administrative staff college here, engineering staff college of India, SKI people here, and they were talking to me all sorts of things about why should we do data or what sort of assumptions on data and things like that. But that is a little different. Okay. Anyway, does this help, guys, today? If you have some time, I can talk about something else, but otherwise we'll leave. How is it? Was it okay?
Yep. Thank you, sir.
Thank you, guys, and thank you. So everybody can go ahead. I think people have logged off, which is good. People have left or people are still there. Okay. See, the one quick thing I wanted to say, and this is not related to this is related to machine learning, but I just wanted to quickly mention this because I'm not so sure if I'll remember it again to talk to you guys, which is what? See, we are all in this area of machine learning, right? So what are we trying to do? We're trying to say, given some data, I'm trying to learn something useful from it, right? That's the big picture sort of drama that we are all doing. Given some data, there is some inherent knowledge in that data or pattern in the data which is useful, which we want to learn. Now the question really becomes, If I give two people, if I give Raju here and I don't know, Madhu or Dheeraj there, the same set of data, if I give data, okay, to both fellows, let us say, I give some to Raju and I give some to, I don't know, Madhu, I'm just using your name, okay? It's nothing
Sure.
that I've got against you. And I put this. Now it is absolutely possible that both of you will come with two different results. Right? Both of you will come with two different results. Both of them will be statistically valid. Both of them may show some sort of statistical significance also for all I know. So which one is right? Okay, how do I know? Is it making sense, the problem as I'm framing? And this is a big problem, right, Madhu? At least in your life, you have studied economics. Yeah, the same data, two economists have diametrically opposite answers, and both seem to get Nobel Prizes also. So what do you do in this case, right? How do you solve this problem? And this is a problem that we see again and again in machine learning. And I was telling somebody, I was teaching a class, I was saying, we don't really think about this as much as we should. Mostly what do? The implicit thing is you take in some data, you make some assumptions. Unfortunately, usually most of those assumptions happen implicitly. We don't write out those. We say, oh, this data is IID data. This data, I don't know, follows some Gaussian, and whatever is beyond 3 sigma is an outlier. Some such things you will make. Okay. Somebody else will say, no, it probably follows, I don't know, a beta distribution with these sort of parameters. You take a different prior, and you'll get two different answers. Depending on how much iterations you're running. You're running Thompson sampling, he's running something else. So the lesson I wanted to leave with them and with you is, make these assumptions are critical. Please understand what assumptions you're making. Make it as explicitly as possible. Even then I'll tell you, most of the time we will be wrong, because end of the day, these assumptions will require somebody with subject matter expertise to actually make those assumptions about the data. Unfortunately, we won't have that, because and a lot of time on the client side, subject matter experts also will not be half as good as what they should be. So they wouldn't know either. So unfortunately, I'm giving you pretty gloomy news. Make sure you make your assumptions as explicit as possible and get it validated by as many people as possible. That's the only way that you will get to somewhere closer to a result which actually makes sense in the real world. Otherwise, it's very easy to get caught up on complex math and feel excited about it, but it doesn't work. Yeah, so I don't know, this is just a small thing, but I just wanted to make sure I leave it with you guys as you work through the holidays, think about things and all of that, yeah? Hope that helped, guys. Just my thoughts. So, thank you.